All right. So yesterday we have begun a new method of getting solutions for ordinary differential equations, concentrating again on the second order differential equations called the power series method. And we have demonstrated the efficacy of this power series method using a couple of examples. These examples are stuff that you already know how to solve, but just as a proof of concept that this thing actually works. So the way it works is that you plug in a power series on-sorts into the differential equation, assuming, of course, that it is valid to view the solution as a power series. We'll talk a little bit about this today. And then once you plug in this, of course, you can differentiate the power series with impunity by just taking the derivative inside, because it's a term-by-term differentiation anyway, and plug in y prime and y double prime into the parent differential equation, as we have done here for the simple harmonic problem. And then this gives you a recursion relation typically between the coefficients, because a power series is defined by an infinite number of constants. And of course, a second order differential equation can only have two constants at most, as you know very well. So we need to make sure that most of these constants are actually already determined in terms of the constants that appear before them. So for a second order differential equation, there is two floating constants, which we typically call A0 and A1, the first two terms of the power series, and we determine every other coefficient as a multiple of A0 or A1. And this gives you typically two series. One, in this particular case, it gave you a series that had only even powers of x and one series that had only odd powers of x. Okay, so since these coefficients are quite different and the powers are also quite different, the solutions y1 and y2 obtained this way are actually linearly independent of each other, right? So the one cannot be thought of as a simple multiple of the other. And we went ahead in this particular problem and showed that this is indeed cosine and sine in this particular series. Okay, so now notice that this is the feature of this particular problem. You might have series in which you don't recognize what the pattern is at all. For example, today we will solve a problem in which the pattern will be something completely different than what you've seen before, and that's okay. As long as a solution exists and you find it, that's all that really matters. Okay. And then we started our discussion on certain aspects of a power series. And in particular, we started discussing what convergence means and how do you understand it. So we took a typical power series, some f of x equals this particular power series. And we gave an example. Of course, you can have any number of examples. And the way we kind of understood this power series was by splitting it up into a sequence of, a list of sequences, right? So the first sequence had just the first term in the power series, and the remainder we called R0. The second sequence had the first two terms, and the third sequence had the first three terms, and so on and so forth. And then we formally defined a convergent series as one in which this list of sequences is such that as you keep going further and further, it reaches a limiting value. And this limiting value happens for some x equals x1, say, and this sum or value we called as s of x1. And this is where we stopped yesterday. Any questions or comments about any of this before we proceed? Okay. So roughly speaking, what we are basically saying here is that if you look at these sequences, S0, S1, S2, some Sn, Sn plus 1, blah, 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 right? It's an infinite number of terms in the series, so we can construct an infinite number of sequences. Basically, convergence means that beyond a point, you are hitting a limiting value. Of course, we are saying limit n tending to infinity here. As a practical aspect, we have to understand what this really means. So let us understand what this means from a practical standpoint. What does convergence really technically mean? Okay. So when I say that this sequence has a limiting value, which I'm calling s of x1 for some particular value of x, okay, the value of x is also important here, as we will shortly see. Then what I basically mean is that this series can be summed to s of x1 for x equals x1. Okay, so m equals 0 to infinity, am x1 minus x0 to the n. Okay, so this is what I mean. This means that if I look at any particular series Sn, right, Then, since I can decompose this in this way, S of x1 can be written for any n as a sequence S of Sn of x1 plus the remainder corresponding to that particular value of n. Okay, so for example, I can write this series as 1 plus x squared plus x cubed and so on and so forth, right? That is for n equals 0. Or I can think of the series as piecing it up as 1 plus x squared plus x cubed plus whatever it is. The series is the same no matter where I choose to break it. I can choose to break it at 0, 1, or 2, and correspondingly the rest of the terms I'd simply dump in as Rn, the sequence and the remainder. Okay, so when I say that the series converges, I mean the following. Loosely speaking, you can understand this as the following. So suppose if I take some value of n, okay, and then I claim that, you know what, looking at the series to this particular number of terms is enough, because if you add more number of terms, it's really not going to matter much. Okay, that is what you mean, roughly speaking, loosely speaking, right? So how do you translate this in the mathematical language? You translate it as follows. You claim that, look, I want, for example, you take a particular series and you say that you want to construct a sequence such that all this remainder can be thought of as some very, very small number. Even if it is added, it's going to be very, very small. Okay. Now, I will ask you, well, what number? And you can say, I don't know, 0.05. Okay. And then your friend can come up and say, no, no, I want the remainder to be not 0.05. That is too high. I want it to be 10 to the minus 5. And someone else can come up and say, what, 10 to the minus 5? That is still very large. I want it to be 10 to the minus 10. I want the Sn to approximate the series S of x1 such that the remainder, when all the remainder is taken into account, you only get 10 to the minus 10 or whatever it is, right? Now, here's the important point. The point of a convergence series is that all these requests can be accommodated. Okay, so basically all I mean is the following. Suppose if you come in and say that you want the remainder to only add up to 0.05, I will say that, oh, well, I can always do that by looking at this series because it's a convergent series, and I will choose to stop counting at n equal to 25. If I stop at n equals 25, I can assure you that the remainder is 0.05 and nothing more. Then your friend can come in and say, no, no, I want it to be 10 to the minus 5. I said not 0.05. And I will say, oh, sure, I can do that for you. But you have to stop counting, not at n equals 25, but n equal to, I don't know, 78. And someone else will come in and say, oh, I want it to be 10 to the minus 10. And I would say, oh, yes, then you should stop counting at 105 or whatever it is, right? So the point of a convergence series is that you can approximate the series to any level of accuracy by making the remainder as small as possible. So if you turn this equation around, you can write this Rn, the absolute value of this Rn, as S of x1 minus Sn of x1. And you can choose the value of this remainder to be arbitrarily small, such that for some n greater than capital N. What does this mean? This means exactly what I just told you. If you want the remainder to add up to only 10 to the minus 5, then you have to choose an n accordingly. The point of a convergence series is that such an n always exists. You just have to go down the line furthermore if you want a smaller value of epsilon, but it can always be done. Okay, so that is the point of a convergence series. Technically, this is what it means. This means that, you know, if you choose epsilon to be 10 to the minus 3, and it so happens that for this particular series, this happens at n equals, I don't know, 25, then what it means is that every sequence beyond 25 lies between S of x1 minus epsilon and S of x1 plus epsilon. Okay, so it means that all sequences, all Sn beyond n equals n lie at most between S of x1 minus epsilon and S of x1 plus epsilon. Okay, so this is what convergence technically means. Now you can ask another question. Well, what about x1? I've been telling you that for some x equals x1, the series converges. But what is this x1 and how do you find it? So the question is, what point of x where does a power series converge? Okay, again, taking our example of 1 plus x square and so on, you know that you can always sum this as 1 over 1 minus x, but you cannot always sum this as 1 over 1 minus x. You can sum this as long as x is a small number, right? As long as x is less than 1. Then this sum is meaningful because this is actually a convergent series. If x is 10, there is no way 1 plus 10 plus 100 plus 1000 plus 10,000 is 1 over 1 minus 10, right? That doesn't make any sense. So that is a divergent series. So the question is, how do you understand what value of x admits a power series? So let us look at this series, some series S. Okay. M equals 0 to infinity, am x minus x0 to the n. Suppose if I can write a power series of this form around some x is equal to x0. Suppose if I choose my x1 as x0 itself, suppose if x equals x0, then what is this series? Does the series converge? Of course it does. In that case, for m equal to 0, this series gives you a0, but every other term is 0. So this series does converge for x is equal to x0. And you might tend to think that this is a trivial example, perhaps so, but it can so happen that for this power series, this is the only value of x for which this converges, right? But there could also be other values of x for which this converges, this series converges. This also depends not just on the value of x, but also on the coefficient am. Okay, we'll say a few words about this as we go along. So it might happen that in some series, this is the only value of x for which this converges, but there could also be a range of x values for which a series can converge. Okay. So if there is a range of x values for which the series converges, we can define a what is called a radius of convergence R. Okay, basically we say that the series converges for x minus x0 less than R. Okay, so what I mean is the following. So suppose if this is all my x values, okay, and this is my x0, and let us say this is x0 plus R and this is x0 minus R. Okay, then what I'm claiming is that in this range, okay, so in this range, the series converges. Okay, and beyond this point, here and here, the series diverges. So it could so happen that you have a finite length of x for which a particular series can converge. In other words, the sequence has a limit and the series can be summed exactly. And beyond this radius of convergence, the series actually diverges. So x minus x0 less than R defines the radius of convergence. And obviously, if x minus x0 is greater than R, the series diverges. Okay. So in this particular example, we have that for x less than 1, between 0 and 1, the series will converge. But for x greater than 1, the series will diverge. Okay. And looking at a particular series, there is a couple of ways in which you can actually tell if a series can converge or diverge. As I told you, it crucially depends on these coefficients am. And there is two ways to test convergence. One way is to look at this particular limit. the mth root of the coefficient am in the limit m going to infinity. But what is more commonly employed is what is called the ratio test. The ratio test is basically trying to tell you how the coefficients grow as you go further down the series. So look at the absolute value of the coefficient of the m plus 1th term divided by the mth term. And this ratio gives you the radius of convergence. Okay. So loosely speaking, if modulus of am plus 1 over am is less than 1, the series will converge, because you're guaranteed that as you keep going further and further away, the coefficients become less and less important. Okay. So again, you can test this for the series that we just wrote down, right? So if f of x is 1 plus x squared plus x cubed plus blah, 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 obviously, am plus 1 over am in this case is just a constant, because all the coefficients are just 1, which means the radius of convergence is 1 over 1. It doesn't matter if I take the limit or not, because there is no non-trivial m dependence in this case. So it converges for 1. So this is exactly what we found, right? So beyond 1, it does not converge. Let us take a slightly non-trivial example. This is the exponential series. Okay. So what is this exponential series? This is basically 1 plus x squared over 2 factorial, and so on and so forth, which I can write as, yeah. So in this case, what is the ratio of the m plus 1th term over the mth term, the absolute modulus? The m plus 1th term, remember that I'm looking at the coefficient of x to the m plus 1 and the coefficient of x to the m. The coefficient of x to the m plus 1 in this case is 1 over m plus 1 factorial. And the coefficient of mth term is basically 1 over m factorial. So this is basically m factorial over m plus 1 factorial. And since m is basically a positive integer, I can get rid of the modulus sign, and this is basically 1 over m plus 1. Okay. So now to test the radius of convergence, I will say R is 1 over limit m going to infinity of 1 over m plus 1. And what is this? This is actually
infinity.
This is infinity. Very good. Which means that this series converges to all values of x. This series has a radius of convergence that is infinite in extent. Okay. So in some sense, this is the power of the factorial. So this is in some sense the best case scenario, right? Suppose if I construct a series that is completely opposite. For example, if I look at a series like some g of x, instead of the m factorial appearing in the denominator, suppose if I construct the m factorial in the numerator. Okay. Now, if I apply the ratio test, what will I get? In this case, am plus 1 over am would be m plus 1 factorial divided by m factorial, which will be m plus 1. Okay. Now, if I look at R, it will be limit m tending to infinity of m plus 1, which is 0. What does this mean? This means that this series can only converge for x is equal to 0. For x is equal to 0, obviously this series can be summed to 1 because only the first term survives. For any other value of m, this series diverges. Okay. So you should be careful looking at the convergence and divergence when you're asked to calculate the radius of convergence. Okay. So why did we go through all these things? We went through all these things to tell you basically when you can write down a power series solution for a given ordinary differential equation. When do power series solutions exist? They exist. Suppose if I write the differential equation in the standard form, make sure to always write it in the standard form. Okay. If P of x, Q of x, and R of x have power series representations around some x is equal to x0, then the solution will also have a power series representation around x is equal to x0. Okay. So there is a slightly different way in which this is usually stated, and this uses the notion of what is called analyticity. So have you guys studied complex analysis? A bit of complex analysis, and do you know what an analytic function is?
Yes.
Yes. Okay. All right. So I will use the notion of analyticity at a slightly reduced version of this, because I'm not really going to talk about complex functions. F of x, a function f of x, is called analytic at x equals x0 if it can be expressed as a power series in x minus x0 with positive radius of convergence. Okay. So this is all I mean by an analytic function. Okay. So of course, when you actually do complex analysis, you have to look at Cauchy-Riemann conditions and make sure that Cauchy-Riemann conditions are satisfied and so on and so forth. But of course, inbuilt in all this is the simple assumption that, if you have a function of a complex variable f of z equals 1 over z, this function is certainly not analytic at z equal to 0 because it blows up, right? So it doesn't admit a power series solution around z equal to 0. So this is the notion that we import in the case of real functions, and we simply say that f of x is called analytic at x is equal to x0 if around that point I can express it as a power series in x minus x0. Okay, so at least in some region close to x0 it has a power series representation. Now this representation might fail beyond some x0, beyond some value, and that is fine. But as long as I stick my attention to this small region around x is equal to x0, if P of x, Q of x, and R of x have these power series representations, then of course the solution y in this equation can also be written as a power series representation. Okay, I'm not going to prove this, I'm just simply going to state it. Have you guys studied Lorentz series and things like that in complex analysis? Have you studied series representations, and does this all make sense, and do you connect it to these things or no? It's fine, because you don't need any complex analysis to understand. I just wanted to know if all this sounds familiar, that is all. Anyway, so for this particular course, at least take this for granted, because I'm not going to prove it. So as long as these functions that appear in the differential equation admit power series representations around some value of x, then around that same value of x, I can write the solution as a power series. So to give you an example, and this example is what we will look at in detail. Suppose if you have a differential equation of the form 1 minus x squared y double prime minus 2x y prime plus n plus 1 y equals 0. Okay, so this is called the Leshondar equation that we will study in detail. First of all, in this case, what is P of x and Q of x? So you should be a little careful. You should not jump up and say that P of x is minus 2x and Q of x is a constant n times n plus 1, because this equation is not in the standard form. So first put it in the standard form. So divide through by 1 minus x squared y double prime okay, so this is written in the standard form. Of course, in this case, R of x is 0. Excuse me. And now you look at these functions, and you can quickly satisfy yourself that around x is equal to x0, everything is fine. So this guy can be written as a power series around x is equal to x0, because you can simply use the binomial expansion, right? So write the expansion for 1 plus x to the minus 1 times 1 minus x to the minus 1. And this is a perfectly valid power series representation around x is equal to 0. Similarly for this term. So I can conclude that and nothing blows up at x is equal to 0. Of course, I cannot look at x is equal to 1 exactly. I should look at values less than x is equal to 1. But as long as I confine my attention between x is equal to 0 and 1, both p of x and q of x in this case have power series representations. So I can write the solution of this equation as a power series around x minus x0, where x0 is 0. So the solution can be perfectly well written as am x to the m. Since x0 is 0, I can simply write this as x to the m. So this is a valid power series representation for this particular equation. Okay. So, but there is two things to worry about. First, look at the equation and find out what p of x, q of x, r of x are by putting it in the standard form. Then once you put everything in the standard form, look at any demons hiding. So if you expand this particular, this particular differential equation, I cannot write a solution of this form, right? Because at x is equal to 1, everything is blowing up. So x is equal to 1, this p of x and q of x does not have any power series representations. I should be a little careful in figuring out what the power series representation is. Okay, so this is a question we postponed yesterday because I wanted to tell you how power series solution work in practice. But you should also understand under what conditions they are useful. Okay. So before we move on to Leshondar equations, any questions about any of this? So testing for convergence and looking at the coefficients and taking m equals m to infinity and testing the ratios. So all these things are fairly routine, so you should look at it carefully. Again, we will do this ratio test for the Leshondar equation also as we go along. But for now, I want to switch gears and talk about the Leshondar equation if there is no other questions. Okay. So this will occupy us for a couple of lectures. And we want to talk about a very important equation in engineering and physics. Okay. Called the Leshondar equation, the Leshondar polynomials. So the equation is what I just told you, right? 1 minus x square y double prime minus 2x y prime plus n plus 1 y equals 0, where n is some constant. Okay. Now we will talk about n as we go along. It turns out that the equation actually simplifies if you choose n to be integers. But for now, n can be anything. Now, if n is 0, of course, it's a trivial equation to solve. I leave it to you to solve it. Okay, so if n is 0, this is not even a second order differential equation anymore, because this guy is the differentiation of this guy. So you can write these two terms as ddx of 1 minus x squared times y prime, which you can trivially integrate. So n equals 0 things are very easy, but for non-zero n's, this equation can be a little tricky. So we will, since we have already shown that this admits a power series solution around x is equal to 0, that is what we would try and find. So I'm going to assume that I can write the solution as a power series around x equals 0. And simply substitute this on sorts in the differential equation. So y prime, again, I will write these things pretty fast, but if you have any questions, please do stop me or write it in the chat box. Okay, where I'm assuming that I can differentiate this series term by term. And y double prime is obviously m minus 1 x to the m minus 2. And I should substitute all of these things into the parent differential equation. And the only complication that you have to watch out for in this case is that the coefficients are not constants. So the x dependence arises because of these x dependencies also. So you should watch out for them. Okay, so you should construct the series carefully. So we will do this in steps very slowly. Please follow along. So if I substitute all of these things, this becomes 1 minus x squared times m equals 0 to infinity am x to the m minus 2 plus, sorry, minus 2x m equals 0 infinity am m x m minus 1, okay, plus n plus 1 am x to the m equals 0. This is a homogeneous differential equation. The right hand side is 0. Okay. Now look at the first term. The first term is actually two different series, right? The first series is 1 multiplied by whatever that series is, and the second series is x square multiplied by whatever that series is. So let me write this as two different series. The first series is m equals 0 to infinity am x to the m minus 2 minus, what is the second series? It is x square multiplying this guy. Now, if I take x square inside the sum, which I can always do, I'm simply multiplying all the terms by a factor of x square, but all the terms have x to the m minus 2. So x to the m minus 2 times an x square will give me just an x to the m. So the second series is am m minus 1 x to the m. Okay. Again, please let me know if this manipulation doesn't make sense. The third series is this guy. Again, I take x inside and I get x to the m minus 1 times x, which is x to the m, right? So the third series can be written as minus 2 am m x to the m. And of course, the fourth series can be written as plus n plus 1. Okay. Now I want to massage this equation into something that looks like something times x to the some power equals 0. Now look at the second term, third term, and fourth term. They're already in the form that I want. It is something times x to the m equals 0. The first term is the offending term, but not really. The first term has something times x to the m minus 2 equals 0. But if you look at this first term, m equals 0 to infinity am m minus 1 x to the m minus 2. Notice that for m equals 0 and m equals 1, this series doesn't have any contributions, and this series starts at m equals 2. Okay, so at m equals 2, the first term is of course a2 x to the 0. So I might as well, just like I did for the simple harmonic equation, differential equation, I can shift the series by saying m goes to m plus 2. Okay. If I do that,
sir.
yes.
I don't know if it's just my problem, but I can't see what you're writing. Like it's not updating in the
Oh, really?
notepad.
Okay, so does everyone else have the problem? Because it seems to work for me. Anybody else has the same issue?
Sir, after you wrote the series expansion, like 1 minus x square into sigma minus 2x into sigma, after that I only see 1 sigma. After that, nothing else.
Yeah, same here.
Okay, so what I will do is I'll stop share and reshare. Maybe that will work. Okay.
Okay, sir.
How about now?
Yes, sir, now it's
Yeah, it's working.
So I'm going to erase the bottom portion. Does it work?
Yeah.
Okay, good. All right. So can we continue?
Yes, sir.
All right. Thank you. So this is the series that I had by plugging in my onsorts into the parent differential equation. And now I'm looking at the first term a bit more carefully. So look at the first term. Okay. So if I write this series out in grotesque form, what does it look like? Well, m equals 0 is 0. M equals 1 is 0. So this series starts at a2 plus a3x. Sorry, not a3x. So if I put m equals 3, I get 3 times 3 minus 2, which is 6. So 6a3x, right? Plus, if I put m equals 4, I get 4 times 4 minus 3. sorry, 4 times 4 minus 1, which is 12a4 x square and so on and so forth, right? So I might as well shift m to m plus 2, okay, in this series and write this series as a m plus 2. If I put m to m plus 2, the first term becomes m plus 2. And the second term, which is m minus 1, becomes m plus 2 minus 1, which is m plus 1. And this guy becomes x to the m. Okay. Again, if you don't agree with this redefinition, write down the series again in all its glorious fashion. At m equals 0, the first term is x to the 0, and you have, if I put m equals 0, I get a2. Wait a second, it doesn't really match, does it? Oh, here I should also have a 2. Because if I put m equals 2, I get 2 times 2 minus 1, which is 2. So here, if I put m equals 0, I get 2 times 1, which is 2, right? If I put m equals 1, I get a3. 2 plus 1 is 3. 1 plus 1 is 2. So that is 6x plus, if I put m equals 2, I get 4 times 3, which is 12. a4 x square and so on and so forth. Okay, so you can see that the series matches term by term. So this redefinition doesn't really change anything about the series at all. This is just a convenient way to repackage the exact same series. Why am I doing this? I'm doing this because now every term in this series looks exactly similar. So now I can write this entire series as m equals 0 to infinity. The first term is whatever I've written here, a m plus 2 times m plus 2 m plus 1, okay, minus or plus side, what is this? So minus am times, I can pull am from the second term, third term, and fourth term. So the second term gives me m minus 1 am. So this is m minus 1. The third term gives me a minus 2m. So that becomes a plus 2m because I've pulled out the minus sign already. And the third term gives me a plus n minus 1. So I should have a minus n plus 1. And the whole thing multiplied by xm equals 0. Okay, so this is my differential equation. So again, the first term arises because I've done a small redefinition. So this is why my coefficient is not am, but am plus 2. And this is not a glitch. This is exactly what I want. This will help me write down the recursion relation. The second, third, and fourth terms are all proportional to the x to the m and am. So I've pulled out a factor of am. And assuming I've not made any negative sign mistakes, the first term is positive, the second term is positive, the third term is negative. Okay. So again, this is a whole bunch of x powers of x all adding up to 0. And the only way this equation can make sense is if whatever is multiplying it term by term is 0. Otherwise, every coefficient of x is going to be 0. That is the only condition under which this equation holds true. So this tells me that am plus 2 times m plus 1 times m plus 2 has to be equal to am m minus 1 plus 2m minus n plus 1. Okay, so this gives me a recursion relation because it connects the coefficient am plus 2 to the coefficient am. Now notice that it doesn't connect the coefficient am plus 1 to am. It connects the coefficient am plus 2 to am. Okay, so this is a characteristic of second order differential equations because you need two constants and two linearly independent solutions. So again, just as we did for the harmonic oscillator problem, if I fix m to 0, all my even coefficients are going to be given as multiples of a0. And if I fix m to 1, then all my odd coefficients are going to be given as multiples of a1. Exactly same as the SHO equation that we looked at in detail yesterday. Okay, so let us clean up this guy a little better. We can leave it as such, but it is usually presented in a slightly different form in a standard way. Okay, So this is basically, there is a minus m and a plus m. So this becomes an m plus 1 minus n plus 1, which I can write as m square minus n square plus m minus n, right? And this, of course, is m minus n times m plus n. The reason I'm doing it out is because I don't remember it. So you don't have to do it every time if you remember already what the form is. So this can be written as, excuse me, this is m minus n. So if I pull out an m minus n, this becomes m plus n plus 1. Okay. So my recursion relation between the coefficients can be written as a m plus 2 equals minus n minus m. I'm writing m minus n as minus of n minus m times m plus n plus 1 divided by m plus 1 m plus 2 times am. Okay. So in principle, you are done. So now that you have the recursion relation, again, fixing m equals 0 will generate all the odd coefficient, all the even coefficients, and fixing m as 1 will generate all the odd coefficients. Let's actually do it out for a couple of terms. So let us choose m equals 0. That means if I substitute m equals 0 here, so I'm generating the even series. So even series. So A2, if I put m equals 0, what do I get? My n is something I don't know. So this is minus n plus 1 divided by 2 factorial A0. My A4 would be minus, I'm going to write m as 2. So this is n minus 2 times n plus 3 divided by 2 plus 1, 3, 2 plus 2. So 3 times 4, A2, right? So this again can be written as, if I substitute the value of A2 here, I will have n times n plus 1 times n minus 2 times n plus 3 divided by 4 factorial A0. And I can keep going, but I'm not mad, so I'm not going to keep going because I can recognize that it looks rather unwieldy. Let us do the odd series also, at least the first two terms. If I plug in m equals 1, I'm going to generate A3 in terms of A1. So A3 equals, plug in m equals 1, what do we get? So this is minus n minus 1, n plus 2 divided by 1 plus 1 is 2 times 3. So which is 3 factorial A1, right? And just to bore you, let us actually do A5 also, where I substitute m equals 3 in this recursion relation. So this is my recursion relation. Recursion relation, as I told you yesterday, is because once you generate one or two coefficients, you can generate the rest by simply using this recursive analysis. A5 would be minus of n minus 3, n plus 4 divided by, 3 plus 1 is 4, 3 plus 2 is 5. So 5 times 4, A3, which again would be equal to n minus 1, n plus 2, n minus 3, n plus 4 over 5 factorial A1. Okay, you should go home and check if, or you should stay home and check if all these things are right. Okay. So then I have written down my solution. What is my solution? My solution is y of x equals A0 times the first term is obviously 1. The second term is minus n plus 1 over 2 factorial x squared. My third term is plus n plus 1, n minus 2, n plus 3 over 4 factorial x to the 4, minus so on and so forth, plus A1 times the first term is obviously x because it starts at m equals 1. The second term is minus n minus 1, n plus 2, divided by 3 factorial x cubed. The third term is n minus 1, n plus 2, n minus 3, n plus 4 over 5 factorial x to the 5 minus so on and so forth. Okay. So after my student days, this is the longest I've written the Leshondar equation, Leshondar solutions. Okay. So you will also do it once or twice. The reason I say this is because there is usually a better way to obtain all these coefficients instead of looking at these recursion relations. Unlike the sine or the cosine, you don't really see a pattern here, right? So there it was very easy for you because if I could go back, where was it? Yeah, here you saw that this A1s and A2s and A3s and A4s, they had a very nice pattern of sines and cosines expansion, right? So you could actually see that this series sums to cosine x, cosine omega x, and this series sums to sine omega x. And this is not a surprise because you already know these are the solutions. Unlike that, these guys don't really sum to anything, right? So it's an unwieldy mess. But don't worry, there is actually quite a bit of stuff we can extract out of this. So before we extract much stuff out of this, let us first look at the recursion relation again and understand what is the nature of convergence of this. Perhaps I can leave this as a homework problem for you. So look at this converge, look at this an plus 2. This is equal to, let me write this again, minus n minus m, m plus n plus 1 am. Okay. Now I told you that to test convergence, you have to take the ratio of the am plus 1th term to the amth term. But notice that if you look at an am term, there is no am plus 1 term. The only other term that you can write down is am plus 2. So the solution splits into two series, right? The first is even powers of x. The second is odd powers of x. But whichever series you're looking at, there is no m plus 1th term as we have defined. Suppose if you look at the series as y equals amx to the m, then I'm claiming that the ratio test is looking at the coefficient of the m plus 1th power of x to the mth power of x. But in a series of this form, if you have the m plus 1th power, then there is no mth power. You only have m minus 1th power, right? There is two factors of x. In other words, what I'm saying is that y of x in this series is basically something like this, right? So the second series, for example, in the second series, if I pull out a factor of x, this also becomes 1 minus x squared plus x to the 4 and so on and so forth, right? So it's an expansion, not an x, but an x square. So when you do the ratio test, what you're actually looking at is the radius of convergence, not an x, but an x square. So you have to be a little careful. Is this point clear to everybody? So when you look at a series of this form and you look at the m plus 1th power and the mth power, okay, and then you say that if this ratio is less than 1, then I can find out the radius of convergence, which is some finite number or infinity, whatever it is. But this is the range in x for which this series converges. Now, if you look at the m plus 2th power and m plus 1th power and mth power here, you're not going to get anything. So what you actually have is the powers in increments of 2, right? So if you look at two consecutive terms, what you're basically getting out of that is the range in x squared that is allowed. Okay, so this slight subtlety is something that you should be aware of.
So is that for this equation only or in general?
I do not know if it is in general true. Let us actually investigate a couple of more equations. Okay, in general, all I know is that the solution should always be written in the form of y of x equals a0 y1 plus a1 y2, where y1 and y2 are linearly independent. Okay. So depending on the structure of the differential equation and so on and so forth, you could have different things. For example, in this equation, is it possible that if I had a different x dependence on the coefficients, my series will look different? Obviously it will, right? But whatever it is, there is this notion. The only thing that you should be aware of is that the two series you get should not be simple multiples of each other. In this case, they are not, right? The first has only even powers, the second has only odd powers. That is the only thing that you should look at carefully. Is that okay?
Yes, sir.
All right. So I leave it to you to do the ratio test. Do the ratio test yourself. So take the m plus 2 and the mth term and take the, oh, let's actually do this. It's not very difficult. We have a couple more minutes, right? What is this? Since I take the modulus, this is basically n minus m plus 1 and m plus n plus 2 divided by, oh, this is rather unwieldy. So let's write it here. Okay. So since I'm going to take the modulus, I'll get rid of all the negative signs and so on and so forth. So I'll have n minus m minus 1, the a m plus 2th term, sorry, m minus 2 times m plus n plus 3 divided by m plus 3 m plus 5, no, m plus 4. This is am plus 2 divided by am n minus m plus n plus 1 divided by m plus 1 m plus 2. Okay. Now, even though this looks very, very complicated, notice that to test the radius of convergence, you have to take the limit where m goes to infinity, right? So limit m goes to infinity of this guy. The limit m is very, very large. The other things don't matter, right? So I can neglect the n's and the 2's in relation to m. Now, what do I get? What is the numerator? So if m is very large, I can neglect m and I don't have to worry about the negative signs, remember, because I'm taking the absolute value of this. So I'll neglect n no matter what the value of n is. N is an input, external input, right? So this becomes basically an m square divided by m square divided by m square over m square, which is just 1. So the radius of convergence for this guy is 1. But what I'm basically claiming is that this is the, sorry, this is the region in which it is valid. So R equals 1. And this is not very surprising to you, because even in the very beginning, we asserted that if I put x is equal to 1, this equation blows up. So I cannot expect any power series solution beyond x. Okay, that is the first point. I'll quickly explain what the second point is and stop. This is an infinite series. Okay, it is not a polynomial. Polynomial is a finite number of terms. But notice that n so far has been treated as an independent constant. But if n turns out to be an integer, a non-negative integer, what happens to this series? Look at this. When m keeps growing, but when m hits n, am plus 2 becomes equal to 0. So look at this recursion relation. This is a far more important point. Am plus 2 equals minus n minus m, n plus m plus 1, m plus 1, m plus 2. Okay. Now, if n is a non-negative integer, oops. Then the series terminates. One of these series terminates. If n is even, right, then y1 terminates, because beyond the point m cannot grow. I cannot keep finding coefficients, because as m hits m, n minus m becomes 0. So at m equals m, n, the series terminates. The series terminates at m equals n. Okay. So if n is an even number, then the first series terminates and the second series obviously keeps growing. And if n is an odd number, the second series terminates and the first series keeps growing. So this finite series is this polynomial solution is called the Leshondar polynomial. Okay, this finite polynomial is called Leshondar polynomial. Okay, this usually goes by the name Pn of x. In the tutorial, you will learn a few tricks to generate coefficients of this polynomial, but I will tell you a few more things about this polynomial in the next lecture. Okay, so how to generate this and so on and so forth. We will continue our discussion of Leshondar polynomials in the next lecture. Remember that the general solution is an infinite series solution, but the Leshondar polynomials arises if n is chosen to be a non-negative integer, in which case one of these two series will terminate. Okay, so this polynomial is called the Leshondar polynomial. So we'll stop here for today, and then we will talk more about Leshondar polynomials in the next lecture.